I got everything set up. I can see my voice is being captured. It's like good. And then I forget to press start recording. Okay, there we go. So we are now recording. All right, question number one. Set A has two elements, a lowercase a and b in it. Set B has lowercase abc in it. Which of the following is true? In this case, A is a subset of B. Okay, there we go. Question number two. Given that the union of the two sets consists of the lowercase letters a, b, c, d, and e, and the difference only has c and e, I want you to check all the boxes where it is possible. Okay, in other words, I give you some constraints, and then you have to work out which one of these scenarios can potentially make this happen. So what you need to make sure is between A and B, we need to be able to find all five elements. And then the second thing is C and E can only be in A but not in B. I think that is a pretty strong constraint. So now we look at this and go like, that is not gonna work because in this case, all of A, B, C, D, E would be in the difference when we only want elements C and E in the difference. So that's not gonna work. This one is also not going to work because the difference is going to be an empty set. The third one, so the third one is also not true because B also has C and E in it. So that means the difference would be an empty set in this case. So the third one is not going to work. This one is also not going to work. This one will work because you can see how A, B, C, D, E, are covered by both sets. So if you look at both, they provide all five elements that we need. But when you look at elements C and E only, they are only in A but not in B. Element A is in both, so that means in the difference, A would not appear over here in the difference. So this is one of the choices. This is the other choice because in this particular case, when you look at the union, it covers all five letters. But when you look at what is in A but not in B, yeah, that's pretty clear. C and E are only found in A but not in B. When we look at this one, it is not going to work because we want C and E only in A but not in B. So this is kind of like the flip side of it. This one will work too because in this case, you can see how C and E are elements of A but not elements of B. And even though there are some additional stuff, but in the difference, um, B, D, A, they can also be found in A, so the difference will only consist of C and E in this case. So are we doing okay so far? Any questions? Nope. Okay, moving on. Number three, choose the correct answer. It is saying lowercase a is an element of a set where the only element in that set is another set that has the element of a. That is not true. Okay, this element of is not true. So we choose false here. Correct. So yeah, so if the left-hand side also has braces around it, then the answer would have been true. Yep. Question number four. A set is a subset of itself. It is true, but a set cannot be a proper subset of itself. So you have to differentiate between subset of versus a proper subset of. Yep, correct. Yes. Yeah, so a set is a proper subset of another set when it is a subset of, but there's also something on the right-hand side that is not on the left-hand side of the operator. Correct. Um, because I didn't assign, variable names, so I can only say, if you do the difference of the right-hand side minus the left-hand side, it should be non-empty. Yep. At least one element. Yep. that would define a proper subset of, yes. All right, question number five. The union of these two is ABC. That is correct. Okay, because everything in the union can be found here and the other way around. So we are good here. Number six. Okay, so we are starting to get into some of the trickier questions. So in this case, it is asking what is the value of the following expression. So the expression is going to give you true or false as an answer. So now the question is, but is it true or is it false? Or it kind of depends on what we use A and B for. Okay, so now the question is, which one of these three should we choose? So because this is an implication, my lazy way of thinking is if I can make this side always false, then the whole thing is going to be true, but I cannot make it always false. So now the question is, if I can make the left-hand side true, can I say anything about the right-hand side? Okay, because if I can, it's not difficult to make A minus B to be an empty set because this means everything in A is also in B. Okay, that's basically what's saying. So if I can make everything in A also in B, then can I imply that A is a subset of a proper subset of B is false? So you just have to figure out two cases. One is it is not a proper subset of. The other one is it is a proper subset of. So do you guys want me to kind of work out the cases? Okay, so let's go check out the cases. No, it is when you need to look at the right-hand side. If you can make the left-hand side true, then you have to look at the right-hand side because true implies true is true, but true implies false is false. If the left-hand side is always false, then the implication is always true. That would be ideal because that's the easy case. But because I didn't say anything about A and B, so that means you have to think of what if A is like this and then B is like this. You have to figure out, regardless or depending on how A and B are defined, what would be the value of the implication. All right, so let me go ahead and work this out. Mouse pad, there we go. And I want to show the question too, because this allows us to kind of look at the question. There we go. Just scroll up a little bit. There we go. All right. So the first one is what if A and B are the same? Okay. They both contain A, B, C in this case. Actually, yeah, let me use X, Y, Z because this way there's no confusion when you're just listening to the lecture. So B also has just X, Y, Z. So if A and B are defined like this, then A minus B is the empty set is true. So this whole thing is true. So now we have to look at the right-hand side and say, okay, so but is A proper subset of B? That is not true, but not false. Okay, let me back up a little bit. If A and B are defined like this, A is a proper subset of B is false, but not false is true. So now we have this, now we end up with a scenario of true implies true, which is true. Are we doing okay so far? For this specific case on the right hand side. Okay, so if A and B are identical, a set cannot be a proper subset of itself. So the proper subset of operator returns a value of false. This is negation, not false is true. So that means, in this particular case, we would end up with true implies true, and the truth table of implication says that is true. So, but then if I change the definition so that A only has XY in it and B has all of XYZ, so in that case, um, A minus B is an empty set. It's still true because everything in A are still in B. So the left-hand side remains to be true, but the right-hand side which is A is a proper subset of B, that is true now. But not true is false. So now we have true implies false, and the implication itself is now false. Okay, so in this case, we have true implies false, and the result of that is false. So that means, depending on what you put in set A and on what you put in set B, the answer can be true or false. There's no easy way to say, oh, this is always going to be true, or this is always going to be false. So that means the answer to this question is, it depends. Are we good so far? All right. The exam, okay, so for those of you who have taken my classes, there's a pattern. The exams are always open book and open notes. So if you forget to bring a truth table with you, that's kind of on you. So that means, okay, so knowing that, okay, ahead of time, what are you going to do? You continuously prepare the material for the exam. Okay, so I think that would be the good way to look at it is you just go like, oh, okay, this seems important. Put it into your study guide or the material that you want to bring with you. If you want to, you can print out all my modules too. Okay, you can print all those out, bring them with you. But the way that I write may not be easy for you to find things. Okay, so that means if you just kind of write your own notes to bring with you, it might be better because one, if you create your own notes, by the time you get to the exam, you may not even need it because it already went through your brain a few times already. Two, if you do need to find something because you wrote it, the chances of you being able to find it quickly is much higher than finding stuff in my kind of writing. All right. So now we move on to question number 7. What is the value of um, A intersect with B equals to A union with B? If that side is true, then A and B are the same. So this one is true regardless of how you define A and B. So this is always true. The reason why this is always true has to do with um, the A union A intersecting with B is a conjunction. A union with B is a disjunction. So if you have an element that is in the intersection and also everything in A and B are both in the intersection and also the union, then A and B must be the same. There cannot be anything that is in A but not in B. Hmm? Say again, sorry. If you do a Venn diagram, that becomes obvious too. Yep. Yep. But it also kind of makes sense, because if these two sets are the same, that means everything that is common to A and B turns out to be everything that is can be found in at least one of them. So just from the perspective of semantics, it seems to make sense that the two sets are the same. Everything in A can also be found in B. Everything in B can also be found in A. And then we move on to question number 8, the last one. Okay, so this one is saying A is an element of B implies it is not the case that A is a subset, not proper, just a subset of B. Okay, so the question is, can I create a scenario where set A is in fact an element of B? That would not be too hard. Okay, so let's go ahead and take a look at how we can make that happen. So in this case, I can make set A to be a really simple one, maybe just the empty set. And then B is anything that is, well, B can be empty too. Okay, so let's find out what happens in this particular scenario. So in this case, A is a subset of B is already false, which means the implication itself is true. So, okay, so I'm just going to describe this. This will end up with a true, false implies whatever, but that is always true. Okay, so that means, I need to now try to find a case where the implication itself is false. The only way for an implication to be false is for the left-hand side to be true, but the right-hand side to be false. So I'm trying to find an example, a case where set A is in fact an element of set B, but set A is not a subset of set B. Okay, so that would not be too hard to do because I can make set A to be just a set consisting of X itself. I can make B a set that consists of a set with only X in it. Is that okay? So in this case, the left-hand side is going to be true because set A is actually an element of set B. So the left-hand side is true. Now I have to evaluate the right-hand side. Ooh, okay, so this is still going to be true because A is a subset of B is false. So this operator returns a false, but not false is true. Okay, okay, not quite, but that gives me an idea of how to make that work because all I need to do is to make sure this subset of is also true. That would be actually pretty easy. Huh? It is not a subset. So this is false, but not false is true. Because I put a negation on the outside. Yep. All right. So that would not be too hard to do. All I need to do is to make a slight adjustment where set B has the element of X itself and also a set that has X as an element in it. All I have to do is to add one more element to the whole thing. So now the left-hand side continues to be true because um, this element continues to exist in B. So A is an element of B continues to be true. But the right-hand side is now false. The right-hand side is false because in this particular case, A being a subset of B is also true because everything in A, which is only lowercase x itself, can also be found in B. So A is a subset of B is also true, but not true is false. So I end up with a true implied false. When you look up the table of implication, then the operator returns false. So that means it depends on what you put in set A and set B. It can be true or false. So this one also goes to depends on how set A and B are defined. Is that okay? Oh no no no. We are just warming up for this semester. We're just warming up. Um yeah. So but you can see how I try to solve the problem, right? I can okay, I can make this true. So now the question is can I make it false? In the case of an implication, to make it false, there's only one way to make it false. The left-hand side is true, the right-hand side is false. So now the question is, can I make both of them happen? Okay, so that depends on your understanding of the set operators to kind of quickly find a test case to make it happen. All right, well, let's see whether I'm getting a perfect score or not. And what is my score? There we go. 10 out of 10, I think. I think it's worth 10 points in total. So I think I got, well, we can just look at the color too. Yep, I think I got it. Cool. All right. So are we ready to move on to talk about functions? All right. So the reading material is, oh, okay, before I forget, there's also a homework assignment for next week. In this case, it's due on Monday, okay, because we need those concepts to be all clear before we can talk about injection, surjection, and bijection. So that's why just function is due on a Monday. That still gives you like what, four more than 4 days to work on it. Okay, so the key is to get started early. Okay, get started early. So this one is your new homework assignment. But what we're going to be talking about is functions as sets. And I think the module is already up. Yep, there you go. So this is module 0289, which is already integrated into the GPT-TA. So if you go to the GPT-TA, it already understands this particular module. And this whole thing starts with the discussion of tuples, and it's nothing new. We already talked about tuples when we talked about the Cartesian product. So a tuple is a ordered container where its components are ordered. So that means the tuple 1, 1, 2 is different from the tuple of 1, 2, 1. Now this example also shows you that you can have duplicate values in a tuple where you cannot have duplicate values in a set. Okay, so it serves to differentiate tuples from a set in two ways. One, ordering is important because 1, 1, 2 is not the same as 1, 2, 1. And then the second one is you can have duplicate values in a tuple. And the best way to think about tuples is it is just an array. Okay. And the rest is really just saying, okay, how do we denote a tuple? It is just a bunch of stuff separated by commas in parentheses. Okay. And then there's a little bit more notation where if T is a tuple, then T bracket I or T subscript I is referring to the item at index I, which is zero oriented. So it's kind of like it really is just like arrays. Okay, you're just indexing into a particular element in a tuple. There's no indexing into a set because there's no ordering. You cannot say, oh, this is element zero. No, because there's no intrinsic ordering within a set. But within the tuple, everything is ordered, so you can always say, okay, this is element zero, element one, element two, and so on. So are we doing okay in terms of the concept of a tuple? It is ordered. It's always ordered. The next one, you mean this one? It is ordered. So in this case, element 0 is a 1, element 1 is a 1, element 2 is a 2. In this case, element 0 is a 1, element 1 is a 2, and element 2 is a 1. It makes it different. Think of these as two arrays. So in the first array, you have element 0 being a 1, element 1 being a 1, element 2 being a 2. In the second array, you have element 0 being a 1, element 1 being a 2, and element 2 being a 1. Those two arrays are not considered to be the same as each other. Yep. All right. Are we okay so far? Okay. So now we look into functions, because in order to define a function using a set notation or set concept, we have to understand tuples. But before we get that far, I'm just going to remind people what a function is in a math class. So in a math class, okay, this is not even linear algebra. This is or calculus. You can define function f of x to be just 2x. In other words, it really is just a convenience. Okay, you basically go like, what is f of 6? F of 6 is 2 times 6, which is 12. Okay, so it really is just a template so that you can refer to um, an expression that involves a variable so that you can go like, okay, what if that variable is this value? Okay, the expression comes back with this particular value. So that's how we use functions in a math class. In this class, we look at a function as a discrete map from a domain to a codomain. If you're already kind of familiar with math concepts, what we refer to as a codomain is also known as range in mathematics. But I don't use that term in this class. I just use the term of codomain, but it really means the same thing as the range when we talk about domain and range in math. And then we look at this particular symbol here, okay? So this particular notation is not confirming anything. In fact, it is a question. Okay, it is asking the question of is f a function where x as a set serves as the domain and y is the codomain. That's what it's asking. So the answer to that question is either true, yes, f is indeed a function using x as a domain and y as a codomain, or false, it is not the case. Which begs the question of, so what exactly is f and what qualifies as a function? Okay, so keep those questions in your head as we try to clarify the rest. So if you have a f of x equals to 2x and you want to express it in this particular way, which means this element maps to that element, this element maps to that element, then we can conclude that function f, if you limit the domain to be all integers, then the codomain is also going to be all integers. In this class, except for very few cases, we don't really deal with real numbers. We deal with mostly integers and natural numbers. The only time we deal with real numbers is when we have to, when it's almost at the end of the semester when we talk about Dijkstra's algorithm and the A star algorithm, in which case the um, distance of an edge can be a real number. But for the most part, we are not dealing with real numbers. We only deal with integers and natural numbers. So in this case, I'm claiming that if 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 this function is applicable to only integers as x, then we have a function f so that the domain would be all integers, and then the codomain would be also just integers. All right. So what is Okay, so in order to get to this part here, you kind of have to remember the title of the entire thing. Okay, the title of the entire thing is functions as sets. So in other words, how do we express a function where it used to be something like this in a set? Well, it's pretty easy. It would be a set of two tuples. The first item of the two tuple is telling you where it's coming from, and then the second item of the two tuple is telling you where it's going to. So in this case, we have mapping 0 to 0, we have mapping 1 to 2, we have mapping 2 to 4, 3 to 6, and so on. But you guys already know that how much I do not like this kind of notation where you have the ellipses to say etc., etc., etc. Well, but that's not clear. Okay, we don't know exactly what is after this. So that means it's better to define it more like this. Okay, so now F is defined to be a set, okay, because of the curly braces, where each element has the form of x and 2 times x itself. And then we have some extra constraint where x has to be an integer. Are we doing okay so far with that notation? So this is why, the notations that we have already introduced earlier in set notation is important because I use those again. Okay, there is a particular way why I introduce the topics in a particular order. It is all based on dependency, which is also a reason why I do not use textbooks, not even Zybooks, because in many textbooks, including Zybooks, the order where they introduce concepts is out of order. At least in my mind, they would talk about something and then they go like, "Oh, right, we haven't really talked about that yet." I am really I don't like that. Okay, I like to introduce concepts where things that you need to depend on would have been discussed already by the time we define new things using those existing concepts. Hmm? Yeah, well, thank you. Zybooks, the raps from Zybooks have been trying to get me to use their books for some time. They sent me an email. They were trying to convince me OER is bad because it's not engaging and you know and all that other stuff. Yep. Yeah, they actively try to get people to use their products. And But I'll address your question in just a moment. They would also mention who else in the department is are already using Zybooks. So they will mention Brian Hermley, yep, and so on. So they go like, hey, these colleagues of you are already using Zybooks. You should be using those too because your students like it. Sorry? Well, I can make my own. I have my GPT-TA to do exactly the same thing. All I have to do is to remove that constraint of do not give students the direct answer. I can homebrew all of this stuff. Yeah, it's easy. It's easy to do that. It's harder to put in that constraint of let's not just give them the right answer. Okay, let's figure out what they need to understand first and double check that they have all the prerequisite knowledge and competency before we kind of move on. In other words, the GPTTA is supposed to have the dynamic scaffolding capability. That would be a really awesome marketing term. Huh? Yeah, they email that stuff and then they talk about, the negative side of OER. It is not engaging, it's not interactive, and so on. They are good at selling stuff. All right. So, this is just a reminder of if you look at something like this, it really means this. Okay. Yes, go ahead. Sorry, I forgot to address your question. hmm Okay, let me scroll. You mean this one? Uh-huh. Okay. Yes. So if you want to claim that f is a function, you first have to say what is the domain and what is the codomain. And there are some additional constraints, to really say whether it really is a function or not, which is described in section 3.1. This is a question. Remember, this is a Boolean operator as a whole. It is really just asking, is the set f, can it be considered a function mapping from the domain X to the codomain Y? It's really asking a question, is it true or false that f can be considered as a function mapping from the domain X to the codomain Y? So it's really asking a question. Yes, go ahead. The upside down, what again? Sorry. This is for all. No, this one is filtered. So that means, for all X in the set of all integers, for all y, and for all y in the set of integers, this has to be true. It means all. Yeah, this means, for all integer x and for all integer y equals to 2x if and only if xy is a two tuple is an element of f. Yep. Yes. Yep. So that's what section 3.1 is about. It will give you expressions to evaluate. If that expression is true, then we establish that f is a function mapping from domain x to codomain y. So section 3.1 gives you the exact condition to evaluate to see if f as a set can be considered as a function mapping from x to y. All right. So the all the sections before are kind of more like relating to things that we have kind of talked about, but they don't give you the actual qualifying conditions yet. And that's the job of section 3.1. All right. So those are all good questions. Any other questions before we move on to section 3.1? Any questions about notations? Any questions about the meaning of things like what is a tuple, what is a subset of, that sort of thing? Nope. All right. Well, if there are no questions, we're going to move on to section 3.1. What makes a function a function? This is just me playing with the name. It really should have been said, it really should have been what makes a set a function. But I just like to kind of play with those phrases. Yep. Go ahead. Hmm? Well, let's go ahead and take a look at the first paragraph and also, what condition has to be true first. Okay. So you probably recognize that a function f, if f is a function mapping from domain x to codomain y, it means then the following has to be true. In order for this to be true, this is a necessary condition. Okay, so in your notes, you can say, oh, okay, this is a condition that has to be true in order for this to be true. So there's a big difference between what is a necessary condition versus what is a sufficient condition. In this case, f being a subset of the Cartesian product between x and y is a necessary condition. In other words, if x is not a subset of the Cartesian product between x and y, forget it. F cannot possibly be a function mapping from domain x to codomain y. Are we doing okay so far in terms of using those terms of what is a necessary condition? Okay, all right. All right, which is kind of what the next statement is saying, except not in notations, but in English. There we go. So in addition to this observation, there's another important criterion for a subset of the Cartesian product between x and y to be a function. In English terms, each element of the domain must be mapped to one and only one element in the codomain. All right, so I'm going to highlight that particular sentence, and then we'll go like, okay, do we actually mean what that is trying to say? What does it mean? Each element of the domain must be mapped to one and only one element in the codomain. Hmm? Okay, so that is correct. Yep. Okay, that's. I think you understand the meaning, except it's exactly. Yep. Yep. Go ahead. That the example of f of x is 2x is a little bit too complex to illustrate the points. So it is actually easier if I were to give you something that is a little bit more spelled out. So for no particular reason, x has two elements, a and b in it. And also for no particular reason, y has, let's say, three elements in it, and we'll have 0, 1, and 2 in it. Is that okay? So, and f, is a set of two tuples. So that means even if f has, a1 and b2, but if it has anything in addition, like 2 by itself, then this f is not a function. It cannot be a function because this particular f is not a subset of the Cartesian product between x and y as they are defined. Yes. Okay, so let's one thing at a time. So I want to clarify why this particular f cannot be a function. It is not a function because it is not a subset of the Cartesian product between set x and set y. Hmm? Say again? We can make it not lonely, and it would still not be a function because 2, 1 as a two tuple is not in the Cartesian product of AB on one side and then 0, 1, 2 on the other side. Because 2 cannot be found in X. Hmm? No. And that goes back to one specific property about tuples. What is it? It's ordered. Yep. In fact, if I want to make this super duper tricky and confusing, I'll just do it like this. Because now it is just the ordering. Because 2 is in Y and A is in X. Okay, so I can now say, yeah, but each element of the two tuple can be found in X and then the other one can be found in Y, but they're in the wrong order. And as a result, 2A cannot be an element of the Cartesian product of X and Y because every element in that Cartesian product must have the first item of the two tuple coming from X, the second item of the two tuple coming from Y. This does not meet that requirement. It's the restriction of it is ordered and everything from the first element has to come from the set on the left-hand side of the operator, and everything on the second element has to come from the set specified on the right-hand side of the operator. It's based on that definition. So this is a good time. Okay, oh, okay, so let's do that and see what happens. Okay, so if we are to switch these two, okay, f is still not a function. Why not? Because now we cannot say that element A, which is an element of the domain, maps to one and only one element in the codomain, because in this case, it maps to one, it also maps to two. Okay, all right, yep. So this particular f is also not a function, considering x is AB and y as 0, 1, 2. But to add to even more confusion, let's do that. What about this? Is that f a function? So now the question is, what do you mean by one and only one? Does one and only one imply uniqueness, or it does not really care about uniqueness? It just means one and only one. It does not imply uniqueness. So this is a function. This particular f is a function where x is the domain and y is a codomain. It meets all the requirements because is A1 in the Cartesian product? Yes, because A comes from X, Y, I mean, A comes from X, 1 comes from Y, we good. Okay, same with B coming from X and 1 coming from Y. So it meets that requirement. It is a subset of the Cartesian product between X and Y. It has met one of the necessary conditions. Does it meet the second necessary condition where we say every element in X has to map to one and only one element in Y? Well, we have to evaluate one at a time. Look at A as an element of X. Does it map to one and only one element in Y? Yep, it maps to one which is in Y, and that's all it maps to. It has met that requirement. Then we look at the other element in X, which is B, and then we ask the same question. Does B map to one and only one element in Y? The answer is yes, it maps to just one. But wait, Tech, they both map to one. I didn't say anything about they cannot be the same. Yes. If I change B to 2, oh, you mean this to 2? It will still work because B is, I mean, 2 is also one and only one element in Y. So it works. Nope. Nope. It says for each element in X, that element of X has to map to one and only one element in Y. So the perspective is on a per element of X perspective as opposed to everything in X. Hmm. So the yes. So when you look at X Cartesian product of Y, it would have A1, oh, A0 first. Okay. So even though elements in the set are not ordered, in this case it's easier for me to do this in a systematic way so I don't miss anything. So B1 and then B2. With yes. Yep. Yeah. Yeah, because each two tuple is just an element of this set. So if you want to go like I want to move this one around so that it is here, not a problem. Okay, you can shuffle all you want within the elements. They're all good. You just cannot shuffle in the element itself, but between the elements you can do it. So you can have inter-element shuffling, but you cannot have intra-element shuffling. Correct. Yes. Correct. But in this case, you cannot switch because X and Y do not contain the same elements. They do not contain the same values. But if X and Y turn out to be the same set, then you can potentially switch. Well, okay, but if you switch, sometimes that switch will make it not work anymore. So we don't want to focus on can we switch or not. We want to look at this from the constraint perspective, which is okay, what requirements does this set have to meet in order for f to be called a function? So we want to continue to look at it from that perspective. Yes, that is not what I said. Okay, I'm trying to be very, kind of picky about how we say that. I said for each element of the domain, it has to map to one and only one element in the codomain. So there's a big difference between that and considering X has to map to something, because X is a whole set. It doesn't map to anything specifically, but each element of X has to map to one and only one thing in the codomain. Nope, this is how we do it. The two tuple sets A from X maps to 1 from Y, B from X maps to 2 from Y. That's how we define the mapping. The first item tells you where it's coming from. The second item tells you where it's mapping to, which was actually what I said a little bit earlier. Is that okay? All right. So the language is actually very important here because I I have to describe things as precisely as possible. This is the English version of that particular requirement, and you can already see what kind of confusion can kind of pop up, because of, okay, I'm not really sure what you mean by one and only one. Is that applying to the whole domain or is it applying to every single one of the codomain? Do we only need one element of the domain to have this property? No, we need every element in the domain to have this property. Okay, so this is already using as precise of a language as possible, but it is still confusing. That's the nature of natural languages. Okay, if natural languages is are precise enough, we would never have mathematical notations. Okay, those notations exist for a reason. And also, if natural language is precise enough in all cases, then everybody can just vibe code and forget about computer science classes. Unfortunately, that is all. Well, okay, let me take it back. Unfortunate for vibe coders, and fortunately for you guys, natural languages are intrinsically ambiguous. Okay, there's no way to really indicate nesting easily in natural language. You cannot just say, "Oh, I put parentheses around things, and that will specify the ordering of things." No, that is not how we say things, right? So that means there can be a lot of confusion of, okay, what you just said, does it apply to this scope level or does it apply to this scope level? People who have not taken computer science classes do not even know what scope is. So they cannot even spot logical problems like, oh, okay, I think I wasn't being precise enough because I didn't specify the scope. No, that concept does not even exist. So think about those things, because cumulatively speaking, as you think about these things and you go like, oh, okay, so that's why vibe coding is not going to work for complex problems, then you are building up your own skill set and also how you can land a job because you can emphasize what you can do that vibe coders cannot do. That may not be an actual issue because I think that whole vibe coding bubble is going to burst way before you graduate with a bachelor's degree. So that may not even be an issue at all for you guys. All right. Um, all right. So all this stuff here, these few paragraphs is really just re-emphasizing what I said already, which is, natural languages are tend to be ambiguous and so on. And this is a notation that we have seen already. It is basically saying for every E in X, I need P of E to be true. Okay, so I can think of an example. So let's imagine X as a set of all full-time professors at ARC, and then P, predicate P, is saying whatever E is an excellent professor. Okay, so now together we are basically saying every professor at ARC as a full-time professor is an excellent professor. Am I bragging? No. I'm asking, is that the case? Because this entire thing is a question that has an answer of either true or false. Are we good so far? Now, in the previous lecture, I also converted something like this into a gigantic conjunction, because this whole thing is a conjunction. Okay, instead of saying for each element of a set, okay, and then we describe who is in the set, so that would be me, Iraj, Ryan, Kakashan, and so on. And then we say, okay, predicate P is just asking the question is E an excellent professor? So that's a really kind of obscure way to do it. It's easier to ask, is Tech an excellent professor, and Iraj is an excellent professor, and Kakashan is an excellent professor, and so on. That gigantic conjunction has to be true in order for this thing to be true. Does that make sense? So it is a important way to look at things in a different way because in this particular case, I just converted a universally quantified expression conceptually into a gigantic conjunction. So in your mind, you go like, oh, okay. So if tech is the only professor at ARC that sucks, that means the universally quantified expression is false. Does that make sense? Yep. Hmm. That will be the expression or statement. It can either be true or false, right? So if you have a white horse in the stable, then it will be false. Even if all of the other horses, like if you have 999 horses that are brown and one is white, that universally quantified statement will still be false because it is trying to say this is true for every horse in the stable. Yep. Yep. If at least one is false, the whole thing is going to be false. Yep. All right. So that is more or less a revisit of the quantifiers which we have talked about already, but it's good to kind of revisit some of those definitions and see how they can be applied. But this is echoing what I was talking a little bit earlier, which is the order of the introduction of the material is important because I introduce the concept that you need to first understand, and then I will introduce concepts that depend on the earlier concepts. So that means, if you look at the if you look at the concept quote unquote tree of this class, it is structured. All right. So now we move on to kind of the derivation of the monster expression or statement that will end up at the end. But instead of just shocking you with that particular statement, I'm just going to say, okay, so how do we express this? Um, for every element in the domain, okay, this is how we say for every element in the domain, or what we think is the domain. It has to map to one and only one thing. So to map to one and only one thing, we can go like, okay, we can describe the mapping as a set, and this is the cardinality operator, which means how many things are in the set, and we need that to be exactly one. Now, do we know how to express the mapping as a set for each element E? Not yet, okay? So but this is how we do the progression. So now we move on and go like, okay, if I give you a particular thing from the domain, we call it E because we have for all E in X. So E already has meaning, okay? It is bound to a specific thing in the domain or what we think is the domain. So this is basically saying each element of this particular set that I'm constructing ad hoc on the fly is going to be a two tuple, where the first item of each two tuple in this particular set is the E that we are talking about. All right. So now the next question is, what do we need to qualify in order for this particular two tuple to be a member of this set? And that's not too hard, which is just this, okay? We are looking for, this is a set where each element is a two tuple EQ. The value of E is given to me by somebody else. Q is quote unquote a free variable, which means you can make Q anything you want as long as EQ as a two tuple is an element of F. E is already fixed. Q is flexible. Okay, so that means give me every element in F that starts with E as the first item of the two tuple. That's basically what it's saying. Okay, so this is the set where I need its cardinality to be one. So this is how we can, so altogether, everything combined is now saying for every element E in what we think should be the domain, the mapping specified by this particular set F to the codomain, there can only be exactly one thing in the mapping. There's only one mapping to the codomain in F, which is basically the same, basically saying each element of the domain maps to one and only one thing in the codomain. Are we doing okay so far with the notations? Yes, you cannot have repetition in a set anyway. What do you mean? Give me an example. Hmm. Well, 1A can only appear once in a set anyway. You cannot have 1A and 1A. You can have A1, A2, okay? So let's go ahead and relate this back to the example that we are working with. Okay, so we'll just go ahead and make this not a function. Okay, so A also maps to 2, okay, like that. So now, if I need to work out, so we will say, okay, I tell you what E is. E is exactly A, which is coming from X. So now when we ask, okay, give me a set where each element in the set is a two tuple in the form of E, um, what was it, Q, such that EQ is an element in F. Okay, so we want to evaluate this, right? So now the best way to evaluate this is to go like, oh, okay, we know what is in F, so we just have to evaluate all those things, one at a time. So now we ask, okay, let me go back here. A1 in F, or in this particular set, we have to give it a name, so I don't have to kind of, so we call it, no, W. Okay, so W is the name of this set. Okay, so A1 in W is true. Right? It is true because E equals to A. So, okay, that starts with A. And um, A1, so Q is 1 in this case. So EQ is in F is true because, we found it. Is that okay? And then we move on to the next element of F, which is B2. Okay, B2 in W is false. Why is it false? Because B is not even E, so that means it doesn't even meet the requirement of EQ. Okay, and then we move on to the last element, which is A2. So we look at A2 in W is true because we have the constraint already that E equals to A. This meets that requirement. We also have an extra requirement of this A2 as a two tuple has to be an element in F. For this particular F, that is also true. So that means at the end of the day, what are the members in W as a set? Exactly these two. A1, oops, A1 and A2 are in it. So now we ask, what is the cardinality of W? It is 2. Does 2 equal to 1? Nope. So we did not meet the requirement that we were trying to satisfy for every element in X. But because one of the things in X is not meeting the requirement, and this is a universal quantifier, that means, okay, we don't have to look any further. F is not a function, period. Is that okay? All right. All right, so there are two necessary conditions for F to be a function. This is one, but we don't even bother to ask this question unless this is already true. So there are two necessary conditions. This is the first one I would evaluate. If this is false, don't even bother with the second one. And if this one is true, then you go to the second criterion, the second statement to make sure this one is also true. If both are true, then F is a function mapping from X as a domain to Y as a codomain. Are we doing okay so far with the concepts? Uh, yes. So if you look at the earlier example, okay, so I can just kind of work out okay, this is boring. We'll try something else. B0. How about that? Okay. So the first question is F a subset of, I cannot use mathematical symbols here, so I'm going to have to spell out. Is F a subset of X times Y? X and Y being defined up there. Okay, so can somebody answer this question? It is. Okay, so this is true. So it has met the first necessary condition. So now we have to evaluate the second necessary condition. So now we have to ask, if I were to construct W, which is EQ, such that EQ, E comma Q is in F in this particular case. So now to um, we have two cases where E equals to A, E equals to B, because both A and B are elements of X. So we have to there are two subcases to evaluate. When E equals to A, we are now basically asking, what is W? When E equals to A, W is going to be the set, W in uppercase, it would be the set with only A2 in it. And the cardinality of W is indeed 1, so it has met that requirement. This particular element from X has met the requirement. Okay, but because the requirement is universally quantified, I need to make sure B also meets this requirement. So now we go like, okay, what about the case when E equals to B? Well, work this out. Okay, in this case, that would be B0. But in this case, the set that we're constructing also only has one single element in it. So now we can now say that we have met the requirement, because for every element in X, the ad hoc set that we are constructing has a cardinality of 1. So this particular F is meeting both requirements, and as a result, this particular F is indeed a function mapping from X as defined way earlier to Y as a codomain also defined earlier. If it does not equal to 0, excuse me, if it doesn't equal to 1, it does not meet the requirement. Okay, so I'll give you one more example. Okay, so I'm going to ask, this time we have A2, and that's it. Okay, this is F. So in this case, if we are to evaluate things, we ask, what about the case when E equals to B? Because B is still an element of X, right? So in that case, W would have been an empty set. And the cardinality of W would then be a 0, which does not equal to what we want, which is a 1. So that means when E equals to B, the requirement that we need for every element has failed. But because at least one element of X fails the requirement, and because we're using the universal quantifier, so that means the quantified statement itself is going to be false. So there are two ways indeed to not meet the requirement. One is less than 1, and the other one is greater than 1. All right, so getting back, so we got a few minutes to talk about why this is even important. It's like this sounds like a whole bunch of definitions just for the sake of defining stuff so I can get paid for teaching this class. Well, as it turns out, if you want to express the correct outcome of a sorting algorithm, given the input has these particular values, and we want to specify what am I supposed to see as the output, it is not quite as simple as you think it is. Or I did not think it was that complicated when I started, to express that. Because you can say, oh, now that I know how to use quantifiers, we can just say something like this, okay? Assuming A is the array, okay, and bar A bar is the length of an array. So now we can say for every index or valid index up to the second last item of the array, an item in the array has to be less than or equal to the next thing. Okay, that sounds pretty reasonable, right? But as it turns out, if this is the requirement, so let's say you are the professor and I'm the student, and you specify this as the requirement of a sorting algorithm, I can do this with a single loop. I just have to initialize all elements of the array to 0, right? Because 0 is less than or equal to 0, which is less than or equal to 0, which is less than or equal to 0. I'm done. I turn in that homework assignment. You go like, that's not what sorting means. I go like, but according to your requirement, according to your specification, my program meets all of those requirements. You cannot not give me the points. In fact, if you deduct any points, I'm going to file a grievance and tell the dean about this. So you go like, oh man, so this is not enough to specify something. So now what we need to do is to specify something like this, where f is a function. So now you say k of something would be the initial value of an element in the array. Okay, so k of 0 would be the value of a bracket 0. K of 1 is the initial value of a bracket 1, and so on. So now you can say for every valid index in the array, we require that to be mapped to some um, original value from the array before you ran the algorithm. Well, even if you add this, I can still cheat my way out of this one. I take the first element out of the initial array and I just copy that all the way through the entire array. Because nobody says anything about properties of this function, I would just make this function map to one single thing, which is 0. So I take the first element of the initial array, copy that value through the entire array, turn in the homework assignment, and say, I deserve full credit for what I turned in, because that is what you specified. Because all you specified is f only has to be a function. There are no special property about this function that you have specified other than it has to map every valid index of the array to a particular value, which is also a valid index. So I just map everything to 0. Okay. So what we are lacking is the vocabulary to say that we need this to be a bijection. Okay, which is the point of the next reading module, which defines what is a injection, what is a surjection. A bijection is essentially the overlap or the intersection of injection and surjection. Okay, so that is going to be the focus of next Monday's lecture, which is also the reason why I have to give you this homework assignment to make sure that you understand what a function is before we basically stack additional concepts and qualifiers to functions. So your assignment is not only to do the just functions homework assignment, but try to read this as much as you can, okay? Because once you have at least an idea of what we are going to talk about, it does make understanding the material easier. As long as you have kind of like a framework of, okay, I loosely understand this has to do with that, that still helps. All right. And that's the end of today's lecture. I did not take roll, so for people who are missing, they're okay for now. Um, do we have any questions? Okay, I do have office hours every day from 8 to 9 from Monday to Friday. So if you get started early with this homework assignment, you go like, okay, I'm kind of stuck. I don't know how to do this. Come to me, okay? Visit me in my office hour and we can talk about this. And no, I do not have Discord. I do not give my cell phone number away. I only do in-person, face-to-face, office hours. Alrighty. Now I can turn off the recorder.